Good morning. All right, so yesterday we started talking about rigid bodies. Today we're going to keep talking about rigid bodies. And in particular, last time we started talking about the inertia tensor. And we showed that the definition of the inertia tensor about a point x naught was this. All right, and so you should think of this as being a linear function of u, which it is, and the integral here is done with respect to the variable x and the mass distribution mu. Okay. And we showed a couple things about the inertia tensor last time. So we showed that we had principal inertias. Okay, and the principal inertias were the eigenvalues of the inertia tensor. And so these were real because we showed that the inertia tensor was symmetric. All right, and then we had principal axes. Which were eigenvectors for the inertia tensor. And because, again, the inertia tensor is symmetric, we know that there's an orthonormal basis of eigenvectors, and we just call any such orthonormal basis principal axes. Okay. And then we had the inertial ellipsoid. And this was an ellipsoid, and we wrote it like this. We took the points in R3, and we represent a point in R3 as a linear combination of these principal axes, which we can do because they form a basis. And then the formula that the coefficients satisfy is the I1 x1 squared plus I2 x2 squared plus I3 squared. Let's make a little 1. All right, so this is solid ellipsoid. Okay. And so what we talked about last time was we talked about you can kind of think of the inertial ellipsoid as being shaped like the inertia of the body, not necessarily shaped like the body. And the inertial ellipsoid allows us to say a few things very quickly about properties of a body. And so one thing that you can talk about of a body is you can talk about an axis of symmetry. Okay, so an axis of symmetry of a body is an axis U. Okay, so that if I take any rotation matrix, may as well make it determinant 1, doesn't really matter. Okay, so if you take any rotation matrix R and it fixes U like that, okay, then it's also true that R of EB equals EB. Okay, and so the idea here is we're going to take, we have this formula that we're going to mainly think about in this definition. Okay, and what does this mean? Well, this just means if you have a rotation that fixes some vector, that just means it's a rotation about the vector. Okay, so it says that any rotation about u maps the inertia tensor into itself. Okay, that's the definition of an axis of symmetry. All right, and it must be every r that satisfies this formula must also satisfy that formula. Okay. And so what you can deduce from this relatively easily you can easily see that axes of symmetry are principal axes. First, and moreover, okay, so think about what this inertial ellipsoid looks like, okay? So the inertial ellipsoid, well, it's an ellipsoid. And now this property, that you take a rotation that maps the inertial ellipsoid into itself, okay, that's a pretty particular property. If you take some randomly selected ellipsoid and you rotate it, generally speaking, that's not going to rotate into the ellipsoid itself, except for the identity rotation. Okay, and so the requirement that the inertial ellipsoid get mapped into itself is kind of non-degenerate. Okay, so when the body has an axis of symmetry, it's non-degenerate. And so if you think about the only way that you can take an ellipsoid and rotate it about some axis so that it for every such rotation that maps into itself is if the axis of rotation is one of the principal axes of the ellipsoid. Okay, but the principal axis of the ellipsoid, you know, just by the definition of the ellipsoid, the way I've written it here, the principal axes of the ellipsoid are also principal axes of the body. Okay, and so what that means is exactly what I've written here. Okay, that the axis of symmetry must be a principal axis. Okay, so that's one thing that's true. But that's not sufficient, okay? Because if you take, again, so now we're going to take an ellipsoid, which, and consider one of the principal axes of the ellipsoid, okay? And our ellipsoid has the property that if we rotate the ellipsoid about that axis, again, it maps into itself for every such rotation. Okay, the only way that can happen is if the cross section of the ellipsoid about that axis is what? Generally, it's an ellipse, right? If you take a two-dimensional cross section of an ellipsoid about a plane that's orthogonal to one of the principal axes, that intersection will be an ellipse. Okay. Now, if it's an axis of symmetry, what is it? Even more specially than an ellipse, it's actually, anybody?
A circle.
A circle is a special ellipse, and so the idea is that the axis about which you're rotating, the cross sections of the inertial ellipsoid are circles. So what does that mean geometrically? Well, what that means is, so let's say that it's the third axis that is my principal axis that I'm talking about here. It could be one or two, but let's just for simplicity choose that. So what that means is that when I take a cross section in the x1, x2 direction, I get a circle. So that means that I1 and I2 must be the same. Okay, so you can easily see that the axes of symmetry are principal axes, and if U is the axis of symmetry, let me say it the other way around. If U is the principal axis, corresponding to an axis of symmetry. Then the other principal inertias must be equal. Okay. So again, in this course, we're not going to be dealing with, complicated rigid bodies. We don't want to spend a lot of time calculating inertia tensors. Okay, so we're going to generally be dealing with simple rigid bodies. And one of the attributes they're going to have is that their principal axes are kind of, you can make simple assumptions. So that the principal axes are easy to figure out what they are. And sometimes a rigid body will have an axis of symmetry, which will, again, make the determination of the inertia tensor simpler. Okay. Now, if a rigid body, so another thing just to sort of generate some intuition about this. So if a rigid body has two distinct axes of symmetry, okay, and distinct here should mean that they, they're not collinear. They don't generate the same one-dimensional subspace. Okay, so if a rigid body has two distinct axes of symmetry, then well, what conclusion must you be able to draw in this case? Well, let's again maybe look at our equation here for the inertial ellipsoid. Okay, so I know that I have an axis of symmetry. Let's say it's again the third axis, and so that means that I1 and I2 agree. But I know that I have another principal axis, which is an axis of symmetry. Let's say it's the first one. Okay, and the first one tells me that I2 and I3 must agree. And so that means that I1, I2, and I3 must agree. Okay, so there's just some number I, which is, sort of the only inertia of the system, and IC of U is simply this number I times U. So in other words, the inertia tensor is just a multiple of the identity. Okay, and so inertially then, your body is very simple. Inertially, it's just a ball, right? A sphere of uniform mass. Okay, that's very degenerate, of course, but it's not so degenerate for bodies to have axes of symmetry, as we'll see. Okay. All right, so those are some kind of tips to help you calculate inertia tensors. So here's another simplification that you can make. It's not actually a statement about the inertia tensor, but the statement is of the following form, that in certain cases, without loss of generality, you can assume the inertia tensor looks like this. Okay, and so if a rigid body undergoes planar motion, and let me be clear about what planar motion means. Okay, planar motion, if you think about it for a second, what it means is, first of all, that there's some point in the body that is restricted to move in a plane. Okay. And let me call that point x naught. So a plane by definition is two-dimensional. Okay, but that's not enough, of course, because not only must the body move in the plane P, meaning that some point x naught moves in plane P, but the rotations of the body are restricted to be rotations about the axis orthogonal to P. Okay, so that's what I mean by planar motion. Okay, so if a body undergoes planar motion, okay, so I have a big long description there of what planar motion means, but if it undergoes planar motion, then without loss of generality, we can assume that the axis orthogonal to P is a principal axis of the body. Okay, so that's another simplification that you can make. So be careful. This doesn't mean that the axis orthogonal to the body is necessarily a principal axis of the body. It just means that you can assume that it is without loss of generality. So let me maybe illustrate that for an example that isn't going to show up on the video, but if you can see me on the screen. So here's my phone. My phone has three axes, principal axes, pretty clearly, or at least approximately, orthogonal to the sort of sides of the rectangle that is my phone. And so my phone may very well move in a plane like so. Okay, and it may rotate about an axis which is orthogonal to that plane, but that doesn't mean necessarily that that axis is a principal axis. Okay, but without loss of generality, for the purpose of the dynamics, you can assume that the axis orthogonal to the plane is a principal axis, and we'll see how that comes out when we look at examples shortly. Okay. So those are some assumptions or some simplifications that can arise, which will allow you to kind of not be able to fuss that much with exactly what the inertia tensor is in simple examples and just kind of write it down. Okay. All right. So now we have some data at hand to say the following thing, kind of an assumption that we're going to make from now on. It's not an assumption you have to make, but life is easier if you make it. So we assume that the origin of the body frame okay, and a long time ago we called that O body, is located at the center of mass of the body. Okay, so now we know what all I've kind of mentioned this as briefly in the previously, but now we have all the words to know exactly what that means. So of course you knew what the center of mass was before, but now you really know. And of course, the body frame moves with the body, so that means that as the body moves around, the body frame is always at the center of mass. Okay, So that makes for some simplifications, and we'll see exactly what those are. Okay, so if I don't say to the contrary, we'll always assume that the body frame's at the center of mass, which you can always do just by moving it. Okay. So let's look at some examples. Okay, so we have our first example is our planar body. Okay, so now it has a center of, so I'm going to draw a little bit bigger so my center of mass symbol shows up. Okay. All right, so there's the usual symbol you use for the center of mass. And so now I'm going to make sure my body frame goes there. Okay, and so what you do is you write the inertia tensor for the body in the body frame, of course. You can write it in the spatial frame and you get some other thing, it's going to, that other thing is going to depend on the configuration of the body. So when you write the body, the inertia tensor for the body in the body frame, that's a constant thing. It just depends on the body. Okay. So we write inertia tensor in the body frame. Okay, and what's the inertia tensor here? The inertia tensor, well, you know, we don't really know that much. You know, the body could have some kind of a crazy shape. And so this is a situation where I'm going to use my fact here, okay, that if a body undergoes planar motion, then I'm going to take the axis orthogonal to the motion, which in this case is the B3 axis. Okay, so I've chosen the B1 and B2 basis vectors for the frame to lie in the plane P that the body moves in, and so B3 will be orthogonal to those. And so I'm going to assume, I can assume that B3 is a principal axis. Okay, so and again, we'll see exactly why this is, but we're not quite there yet. So we can take B3 to be a principal axis. Okay, and so therefore what we're going to do is we're going to assume that all right, so I've already said that I'm going to be taking inertia tensors about the center of mass, and I'll write those as I sub c. Okay, and so I sub c, I know, is a linear map from R3 to R3, and so really now I can write this as a matrix. Okay, normally when we've talked about linear maps and bilinear maps and vectors and dual vectors in the past, we've been very careful to understand that they may have matrix representations, or vector representations, but they're not necessarily matrices or component vectors. Okay, but this one really is. It's a linear map from R3 to itself, and what this says is that there's going to be, so B3 is a principal axis, so that means it's an eigenvector. Okay, so if it's an eigenvector, then I know, in fact, as an eigenvector that everything here must be 0. And then because it's symmetric, everything here must also be 0. And so what that means is that I get 0, 0, and there's some number here, which is the inertia corresponding to the principal inertia that corresponds to the principal axis B3. And then I have stuff here that I don't really care about. Okay, and again, we'll see later why it is we don't care. Okay, so that's what our inertia tensor looks like there. All right. Okay. All right, so we had this other example that we looked at too, but for inertia tensors, it doesn't really contribute anything important. And the reason is that this stupid robot example is planar. Okay, so I have two bodies, and but the motion of the bodies is planar, and so I'm going to get inertia tensors that look just like that. Again, they may not look just like that, but I can assume they look like that without loss of generality. Okay. All right. Now let's look at this other example that we looked at, but we haven't looked at it for a while. This example of a rolling disk. Okay, so it's a nice example where we can calculate its inertia tensor. Okay, so we had a body frame which stuck out of this thing, and it kind of looked like this. And we chose B3 to be here, B1 to be here, and B2 to be here. And of course, my two-dimensional diagram of this three-dimensional situation is defective. But the idea is that B1 and B2 are sort of in the the plane of the face of this disk, and then B3 is orthogonal. Okay. And so I'm going to assume now that the body has a homogeneous mass distribution. And one of the consequences of that is that the center of mass is going to be the kind of rotational center of the disk. Okay, or the geometric center of the disk also. Okay. And it doesn't have to be like that, okay? But if it isn't, then the problem's quite a lot more complicated. But let me make things simple and assume that the disk is a homogeneous mass distribution. And the implication of that is the center of mass is equal to the center of rotation and by center of rotation, I just mean that there's two kinds of rotations this body does, right? It does whoopsie. It does let me get my right hand rule right. It does a roll, and then it does a spin. Okay, and the point is that there's a point in the body that remains stationary as I do those two kinds of rotations, and that's what I mean by the center of rotation. Okay, and this is also the geometric center of the body, if the body's shaped like I wrote it there. Okay. All right. So that's a simplification that I can make, and again, that doesn't have to be true, but if it isn't, then the modeling of this example is actually a lot harder. Okay, so what's the inertia tensor look like? Well, this body is not undergoing planar motion, right? So it is true that there's a point in the body, namely the center of mass, that as the body moves, subject to the constraints that I have here, it remains inside a plane, namely the plane, which is sort of the plane of motion raised by the radius of the disk. Okay, so there's a plane that the center of mass moves in. Okay, so it satisfies one of the two conditions of planar motion, but it doesn't satisfy the other one, right? That the rotations are rotations about the axis orthogonal to that plane. That's not true here. Okay, so this isn't planar, and so therefore I have to think about now what the inertia tensor is. And so let's make if I use this property of that the shape is just like I drew it here, so it's a disk with some kind of constant thickness, and it has a homogeneous mass distribution, what special attributes do you think this body has that will contribute to its inertia tensor being simple to calculate? Suggestions?
Some of the principal inertias will be equal.
Which ones?
1 and 2.
That's right. So what's another way of saying that?
There's an axis of symmetry at
Yeah,
B3.
so B3 is an axis of symmetry, exactly. Okay, so the body axis B3 is an axis of symmetry. Under the assumptions I've made about what my body looks like. Okay, and so therefore, I know immediately from this that the inertia tensor about the center of mass. So it's going to, so B3 is an axis of symmetry, therefore it's a principal axis. And so there's going to be some number down there and zeros here. So I know that. And let me call that number. So that'll be the inertia for rotations, or right, for rolling. So let me call that J roll, because it's the rolling inertia. Okay, and what I know is that the other two eigenvectors, or the other two principal inertias, sorry, the other two eigenvalues and the other two principal inertias must be the same. And so what that means is that that little block there must be some multiple of the 2 by 2 identity. Okay, and so I can put some number there on the diagonal and zeros off. And what should I call that number? Well, that's going to be sort of the inertia for spinning. Okay, so it's going to be about this axis and about this axis. And if you think about that, that means the body is kind of spinning. Okay, so I'm going to call those two inertias spin. Okay, so by simple assumptions, you can turn the inertia tensor for this example into something you can actually just kind of write down. And if the body has a homogeneous mass distribution, you could do some integrals to figure out what the value of those numbers actually are in terms of the mass and the radius of the disk and the thickness of the disk. But let's not get into that. Okay. Okay, so so that's inertia tensor. All right. So now, what do we do with all this stuff? So I've made a bunch of statements at various times about without loss of generality, you can say certain things about the inertia tensor, and I've sort of alluded to the fact that the without loss of generality is with respect to the dynamics. So so let's sort of work slowly towards what that might mean. Okay, so we need to think about the dynamics. And so we're going to write down dynamics for these kinds of systems that we're talking about. But we're not going to do it in the way in which you are familiar. The way in which you are familiar is F equals ma, right? We're going to do write down equations of motion derived using an alternative formulation, which is called the Euler-Lagrange equations, which are equivalent to F equals ma, but are different to calculate. In the Euler-Lagrange formulation for the equations of motion, energy plays an important role. So kinetic energy particularly, and potential energy if your system has potential energy, okay? And so this, the point of that little diatribe is that we're going to talk about kinetic energy. Okay, so kinetic energy of a particle of mass m following a path. Okay, so we all know what the kinetic energy of that thing is. Okay, and the norm here that I'm using is, of course, the standard Euclidean norm. Okay. All right, but what we want to do is we want to talk about the kinetic energy of a rigid body. Okay, so I have a rigid body which is moving. Like so. So my body is the usual lump and mass. It has, so I'm going to put at the center of mass here. It's quite important that this be the center of mass for the purposes of the calculations that I'm going to do. Okay. All right. Okay. So now I have, therefore, of course, that vector r of t. Okay. And then what I'm going to do is I'm going to label points in the body. And, you know, kinetic energy is calculated with respect to the derivative of the spatial position, so the spatial velocity, okay, relative to the spatial frame, okay? And so what I'm going to do is I'm going to take a point in the body, okay, which is a point here. And so I take a point in the body, and then the vector from the body center of mass to that point, I'm going to call that chi. Okay, and the point is that that's supposed to look like x. Okay. All right, and then the spatial position of that point is going to be that. Okay, and I'm going to call that x. And that's going to be now a function of time, right? So chi is a constant because chi is a point in the body and it's measured with respect to the body frame. The body frame moves with the body, so chi is a constant. And so do a little bit of geometry, and you see that the spatial position of that point, which in the body frame is labeled by chi, looks like this. Okay. Right, and so you know, so you're going to translate out to the body from the spatial center, from the spatial origin to the body origin, and then you're going to appropriately rotate the spatial frame and the body frame, and so it's either going to be r of t or r transpose, and so you have to kind of think a little bit about why it's r. Okay, all right. So then, what will the kinetic energy be? Oops, won't be that. Okay, so it's going to be, so I'm going to take this, point chi labeled in the body frame. Okay, and then labeled by x in the spatial frame. And so I know that the just sort of by that kind of reasoning, if I have a little, so I'll sort of think like a physicist for a second, then I'll change into somebody who knows about measure theory. So I take a lump of mass at the point in the body at the point chi, and so that little lump of mass is going to be d mu of chi. Okay, so I think I need more space. D mu of chi, and so this is kind of in my formula here. That's m. Okay, and then it's going to be r dot squared, but r now is the position of that point chi in the spatial frame, so that's x dot of t squared. Okay, and then so that's going to be kind of the kinetic energy of a little lump of mass with that much mass at the point x, and then to get the kinetic energy of the whole body, I integrate. Okay, so that's the kinetic energy of the entire rigid body. Okay, and so then you just do a substitution now. Okay, and so I'm not going to do it today because I want to do the calculation carefully enough that you can understand what I'm doing. If I rushed through it, I could finish it today, but I don't want to do that. So what we're going to do next time is we're just going to slowly and carefully calculate the kinetic energy of the body. So it's a very beautiful little calculation which brings together a lot of different things that we've been talking about. Okay, so we're going to finish a little bit early today. So I'm going to post the announcement on Q about this, but for the quiz today, you have 35 minutes. As opposed to 30, so keep that in mind. And there's also going to be 2 versions of the quiz posted, one for students in 439, so undergraduates, and the other for students in 836, so graduates. So make sure you grab the right one. They're labeled clearly. One is quiz-439, the other one is quiz-836. You can't be confused about that. So make sure you get the right one and you do the right one. So you'll know what you're looking at when the quiz starts today at 1:30. Okay, I will stop the recording.